Hello, Homer back again, and we're just continuing with the section 5.2 slides on slide 28 where I got messed up last time. So wanted to talk about a couple of bad ways to interpret a confidence interval. So we remember we've got a confidence interval for the proportion of all students at Georgetown College who are female that goes from 44.8 to 67.9%. One of the bad ways to interpret this interval is to say that we're 95% confident that the sample proportion is between 44.8 and 67.9%. That's totally not the right way, because we know that the sample proportion is right in the middle of that interval the way we constructed it. That 56.3% sample proportion is right smack in the middle. Given that we already know this, then we don't really need to know anything about sample proportion. Nobody makes a confidence interval for something that you already know from your data. Another bad way to interpret the interval is to say this, that if lots of statisticians took their own samples and computed confidence intervals using our formula, then about 95% of them would get a sample proportion between 44.8 and 67.9%. Again, that's wrong. Our confidence intervals are just trying to capture the unknown parameter. They're not trying to capture what sample proportions might be. I want to talk about the concept of margin of error in confidence intervals. So the margin of error is what you add or subtract from your estimator to get your confidence interval. So when we were making those 95% confidence intervals, then we would add and subtract 1.96 times the standard error of the estimator. But if we wanted a 99% confidence interval, we were adding and subtracting 2.58 times the standard error of the p-hat. In general, what you're going to add or subtract, your margin of error, is going to be a special number z star times the standard error of the estimator that you're using, the p-hat or whatever. And that z star is always chosen to get the desired level of confidence for your interval. So let's take a closer look at the margin of error and dive into the different sorts of things that affects how big it would be. When you're estimating a population proportion, the margin of error has got this form here because the square root of the p-hat times the 1 minus p-hat over the n is the standard error for p-hat. Now notice that the n, the sample size, is in the denominator of the fraction inside the square root. And you know that when denominators get big, the fraction gets small. So the larger the sample size n is, the smaller that fraction will be. Therefore, the smaller its square root will be. Therefore, the smaller the standard error will be. Therefore, the smaller the margin of error will be. On the other hand, the smaller the sample size is, the bigger the margin of error is going to be. You can watch this at work. If you were to run watch statisticians where they're all taking samples of size 100, and let's say the true population proportion is 0.5, let's say you're watching 50 statisticians and they're all making 95% confidence intervals. So when I ran it, the statisticians all basically got intervals about yay wide, where I'm bringing my mouse back and forth. Statisticians who covered the interval, covered the p, and statisticians who failed to cover the p all had about intervals yay wide at sample size 100. Now take a look, same situation, but the sample size is 400. And you'll see again that most of the statisticians are covering the interval, some aren't, but their confidence intervals are narrower. The bigger the sample size, the smaller the margin of error, and therefore the more narrow the confidence interval is. So when your sample size is bigger, you could be more precise about what you think the population parameter might be. Next, let's look at the effect of your confidence level on the margin of error. So remember, the special number z star is chosen to match your confidence interval. It is chosen to create a certain confidence level. And the bigger the confidence level you want, the bigger that z star is. It was 1.96 for 95% confidence. It was 2.58 for 99% confidence. So the bigger the confidence level, the bigger the margin of error is going to be. And the smaller the confidence level, the smaller the margin of error is going to be. You can see that if you were to watch statisticians, same situation as before, except we'll take the level down to 0.8. So we're sampling 100 at a time, and the level is at 0.8. And you can see that the confidence intervals tend to be narrower than they were when the level was 0.95 at sample size 100. 0.95 sample size 100 was back here, wider intervals. Notice that only a few of them failed to contain the parameter. Now, 80% confidence intervals, narrower intervals, but more of them don't contain the parameter. After all, you're only 80% confident of containing the parameter this time. Here we are looking at sample size 100 and 99% confidence intervals. They're all rather wide, and they all contain the population parameter. Only about 1 in 100 of them would fail to do so. I want to talk about the success-failure condition that you see discussed in the textbook. You have to bear in mind that the formulas for our confidence intervals, the p-hat plus or minus, the z-star times the standard error, they assume that p-hat has the normal distribution. But we've learned that for the sample proportion p-hat to be approximately normal, we need that the expected number of successes, that's n times p, has to be at least 10. And the expected number of failures, n times 1 minus p, also has to be at least 10. But we're in a situation where we take samples and we use them to make confidence intervals because we don't know p. So how are we ever going to know that n times p is bigger than or equal to 10? How are we ever going to know that n times 1 minus p is bigger than or equal to 10? We're going to know our n, our sample size, but we don't know p, so we can't figure out these numbers. Well, we can't know for sure, but we can make a guess. I mean, hopefully, p-hat is approximately p, right? So why don't we just check to see that n times p-hat is at least 10, and that n times 1 minus p-hat is at least 10. Now think about n times p-hat. That's n times p-hat, which is the number of successes, the number of people who said yes in your sample, divided by n. The n's will cancel out, and so it's the number of people who said yes to your yes-no question when you took your sample. N times 1 minus p-hat, same math, and if you multiply the n through and use the distributive property, you get n minus the number of successes, and that's the number of failures, the number of people who said no to your yes-no question in your sample. So it really comes down to this. What we'll do before we make any of those confidence intervals is just check to see that the number of successes and the number of failures in our sample is at least 10 each. That's the success-failure condition that you see discussed in the textbook. So as an example, when we were estimating the proportion P of all Georgetown College students who are female, we used that Math 111 survey sample, and we could just check for ourselves. We could tally up sex, data is Math 111 survey, and we find 40 females and 31 males. So the number of successes, the number of people who say yes to the question, are you female, is 40. That's at least 10. And the number of failures, the number of people who said, no, I'm not female, is 31. That's at least 10. So this confidence interval can be trusted to have approximately the level of confidence that it says that it has. So the moral of the story is always check. If you plan to make a confidence interval based on that normal approximation, just check the success-failure condition first. This holds any time that you are making a confidence interval for a population proportion. See you next time.